In this video, we're going to go over some practice problems on the material covered this week. So we're going to start with section 10.4 here. So for question 15 and 24, what we want to do is essentially expand these log expressions here. So we're going to try to write them as a sum or difference of logs or as a single log if possible. And we're going to do so using these following properties of logs here. And so this is a screenshot directly from the textbook here. Now for question 15, we're going to start with the product rule. So that says this is true here. So that means for question 15, we can expand what's in our parentheses here using this on the right-hand side of our equation for the product rule here. So this means this is going to be the same thing as log base 7 of 4 plus log base 7 of 5. So this would be our final answer here. We're just trying to write this as a sum or difference or as a single log. Now for this next question here, for question 24, we're going to be using several different properties. And so we're going to start by kind of just working from the outside here. So as you can see, we have log base 6 of this square root of p times q divided by 7. So on the outside, we have this square root here, which can be written as this pq over 7 to the 1/2 power. Now going back to our list of the properties of logs, we have what's called our power rule here. So it says that if we have log base b of x to this r here, this can be written as this here. So this r, this x, when it comes down in front of our log expression. So we can do the same thing here. We can rewrite this as the following. We're going to have 1/2 in front of our log expression here. All right, now notice we have PQ divided by 7. So going back to this chart here, we can use our quotient rule. So we can rewrite this quotient as this guy on the right-hand side of our equation. So this is going to be the same thing as we have this 1/2, and I'm going to write these parentheses on the outside just to emphasize that this 1/2 is being applied to this entire thing. So we're going to have log base 6 of PQ minus log base 6 of 7, what's in our denominator there. Now we're almost done expanding this. Notice that we can also use our product rule here. We have log base 6 of P times Q. So in our last step here, we still have this 1/2 out front, but we're going to use our product rule. So we're going to have log base 6 of P plus log base 6 of Q, and then minus log base 6 of 7. So this would be our final answer here, expanding this original log expression. Now for the next two questions here, we're going to kind of do the opposite of what we just saw. We have these expanded log expressions here, and what we want to do is try to condense them and try to write them as a single log. So we're going to use our log properties. First, for question 32, notice what we have inside of our parentheses here. We can use our quotient rule to write this as, we're going to have log base A of P over Q. So we can write everything inside the parentheses here as this single expression, and then we still have this guy on the outside. All right, now notice this expression here, we can rewrite this using our power rule. This is going to be the same thing as, we're going to have log base A of r squared. Now lastly, we're taking the sum of these two log expressions, so we can use our product rule. So this is going to be the same thing as log base A of PR squared over Q. So that's how we can use our log properties to write this as a single log expression. Let's do the same thing for question 35 here. So we have log base 10 of this guy plus log base 10 of this guy. So using our product rule, this can be written as log base 10 of x plus 3 times x minus 3. All right, now what we can do is FOIL this, and we can recognize this is actually a difference of squares here. So this is going to be the same thing as log base 10 of x squared minus 9. So this would be our final answer here. We do have two terms here, but we just have one log. So this is going to be considered a single log expression. So for this last question in this section here, we want to determine whether this equation is a true or a false statement. We're going to do so using our log properties. So notice on the left-hand side here, we have the difference of these two log expressions, so we can use our quotient rule here. This is going to be the same thing as log base 6 of 60 over 10. We still have 1 on the right-hand side of this equation. Now we can simplify this. We're going to have log base 6 of 6, and then we still have 1 on the right-hand side. Now from here, we want to see if this is in fact equal to 1. And if we go back to this chart for our log properties, this is one of our special properties here. So we know that log base 6 of 6 will give us 1. So this will be a true statement. All right, so this brings us to section 10.5, where we're going to be using common and natural logs in application problems. So for this first question here, we want to use this formula to find the hydronium ion concentration of bananas, which has a pH of 4.6. So using this formula here, we're going to plug in this value for our pH, and what we're trying to find is this hydronium ion concentration, which is given by that there. So let's plug in our known information. We know the pH is 4.6, and that's going to be equal to this here. So what we want to do is solve for this hydronium ion concentration. Now, in order to do that, the first thing that we're going to do is let's get rid of this negative in front of this log here. So what we can do is just multiply both sides of this equation by a negative 1. All right, so we're going to end up with minus 4.6 is going to give us this positive log here. Now from here, this log here, notice that we don't have a base. So whenever you see, let's write this on the side here, whenever you see a log just like this without a base here, it's understood that this is the same thing as log base 10. And the next thing that we're going to use to solve this guy is a property that we saw in the last several sections here. And it's that if we have an exponential equation of this form here, where we have the same bases in this case, then this implies that the exponents must be equal. So what we can do to get this hydronium ion concentration by itself is take both sides of this equation to a base 10. Doing that, we're going to have 10 to the negative 4.6 is equal to 10 to this log expression here. Now, since this is the same thing as log base 10, we know that these guys are actually going to undo each other. So we're going to be left with 10 to the negative 4.6 is going to give us this hydronium ion concentration. Now what we can do is plug this directly into a calculator here, and we're going to get that this hydronium ion concentration is equal to this here. And to make our lives a little bit easier, we could also write this in scientific notation. So we can move this decimal 1, 2, 3, 4, 5 units to the right. So this will be the same thing as this here. So this is going to be the hydronium ion concentration of bananas. Now for this next example, we're going to be using natural log in a function. So we're told that the time t in years for an amount of money invested at a certain interest rate r to double is given by this function here. So this is the doubling time. What we want to do is find the doubling time for an investment at 5% interest rate. So the first thing that we need to do is convert this 5% interest rate into a decimal. So this will be 0.05. Now from here, we can just plug in this decimal amount into this function. So we're going to have t of 0.05 is equal to ln of 2 over ln of 1 plus this interest rate. So let's simplify what's in the parentheses here. We're going to have ln of 2 over ln of 1.05. Now from here, it's pretty simple. We're just going to plug in ln of 2 divided by ln of 1.05 into our calculator, and this is going to give us approximately 14.21 years. So this one is fairly simple here, just trying to show that we want to solve an equation of this form using our natural log here. We just want to simplify it as much as possible, and then we can plug it directly into our calculator. All right, so for the last question in this section here, we're going to use the change of base formula. So before we get into that, let's write down what this change of base is, and we're just going to abbreviate it with COB. So it says that if we have a log expression of this form here, this is going to be equivalent to this guy here. All right, so it's like base b of a. So we're going to use this to approximate this guy. So we have log base 3 of root 2. We're going to rewrite this using our change of base formula. So looking at this here, in this case, our a is going to be 3, and our x value is going to be the square root of 2. So we can rewrite this as log of square root 2 over log of 3. Now notice we don't have a base here for our log expressions, but that's fine. That means this is going to be log base 10. So we can plug this directly into our calculator here, and we're going to get that this is approximately 0.315. In section 10.6, we're going to be solving exponential and log equations, and we're going to do so using these properties here. So again, this is just a screenshot from the textbook, and so these are the properties for solving exponential and log equations. Now, notice we have 4 properties here, and some of them might seem a little repetitive. We have that if x is equal to y, then b to the x is equal to b to the y. So if we have the same base, then their exponents are equal. Now for the second property, it kind of says the same thing, but it's flipped. Now this is just to emphasize that it does go both ways. Oftentimes in math, if we have a property like this, it might not always mean that it goes the other way. Meaning, it might not make sense that b to the x is equal to b to the y would imply this. However, in this case it does. So listing out the properties like this is just to imply that these properties do go both ways, and the same holds for property 3 and 4. Alright, so let's go back to question 13 here. We want to solve this equation, so we're going to need to isolate x. We're going to need to get x completely alone. Now, in order to do that, we're going to use some log properties. If you remember the power rule for log expressions, that tells us that we can bring down the exponent in front of our log equation, and that would be really useful since our x is in our exponent in this case. So what we can do then to use this property is to take the logarithm of both sides of this equation here. So we're going to take the log of the left-hand side. This is going to give us log of 2 to the x plus 3. And then doing the same thing to the other side of the equation, we're going to have log of 3 to the x minus 4. Now from here, we can use our power rule. So this exponent is going to come down in front of our log. So we're going to have this here, and then similarly on the right-hand side, we'll have this. So now from here, we just want to solve for x. So in order to do that, we're first going to have to expand what's on both sides of our equation here. So we're going to use our distributive property. We're going to distribute this log of 2 to both terms in here, and then the same thing on this side. So we're going to have x times log of 2 plus 3 times log, let's write that nicer, of 2, and this will be equal to x times log of 3 minus 4 times log of 3. Now let's try to get all of our x terms on one side of the equation and all of the other terms on the other side. So what we'll do here is let's subtract x times log of 3 on both sides. And in the same step, I'm going to move this guy over to this side here since we're going to have our x terms on one side. So let's subtract 3 times log of 2 on both sides. So on the left hand side, we're going to have x minus x times log, we're going to have x log of 2 minus x log of 3. On the right hand side, we're just going to have minus 4 log of 3 minus 3 log of 2. Alright, so now notice both of these guys has an x in them, so let's pull that common factor out. We're going to end up with log of 2 minus log of 3, and then we still have all of this on the right hand side. Now our last step here is we're just going to divide by this whole thing on both sides of our equation here to get x completely isolated. So we're going to end up with x is going to be equal to minus 4 times log of 3 minus 3 times log of 2 all over this difference here, log of 2 minus log of 3. Now that we have x completely isolated, we can just plug this whole thing into our calculator, and this is going to give us approximately 15.967. And so we're approximating to 3 decimal places. For this next equation here, we have log base 7 times x plus 3 cubed is equal to 2. So again, we're going to want to solve this equation. So we want to solve for x. So the first step that we should do is maybe try to undo this log base 7 here. So going back to our properties then, we're going to use this property here, this first one. If x is equal to y, then b to the x is going to be equal to b to the y. So let's take both sides of our equation to the same base. Now in this case, we're going to choose base 7, so it'll undo this log base 7 here. So we're going to take base 7 on both sides. We're going to end up with 7 to this power here is going to be equal to 7 squared. Now again, these guys are going to undo each other. So we're just going to be left with this x plus 1 cubed on the left-hand side, and on the right-hand side we'll have 49. Now from here we just want to solve for x, so we're going to take the third root on both sides of this equation. So we're going to end up with x plus 1 is equal to the third root of 49. And lastly, completely isolating x, we're going to get the third root of 49 minus 1 is going to be our solution in this case. And we can plug this into our calculator, and this is going to be approximately 2.659. Now, for question 21, before we solve this guy, we need to recall that the inverse of the exponential function e to the x is going to be the natural log function. So, for example, if we have this equation here, y is equal to e to the x, and we wanted to solve for x, we could just take the natural log of both sides. We're going to end up with ln of y is equal to ln of e to the x. Now we know that these guys are going to undo each other. What's happening here is, so this ln of y here, but using our power rule, this x is going to come down in front, and then we're just going to have ln of e. So these guys are going to undo each other. We're just going to end up with ln of y is equal to x. So applying this to question 21 here, in order to solve for this x, the first thing that we're going to do is take the natural log of both sides of this equation. So we're going to end up with ln of e to the 3x is equal to ln of 9. So our power rule tells us this 3x is going to come down in front, and then we're going to have ln of e. These guys are going to undo each other. So we're just going to end up with 3x is equal to ln of 9. Now we want to solve for x, so we're going to divide by 3 on both sides. So we're going to get ln of 9 over 3. Now from here we can just plug this into our calculator. So this is going to give us approximately 0.732. Now for this next equation here, we again are trying to solve for x. So the first thing that we might want to do is try to undo this log here. Now we can do that by taking both sides of this equation to the same base, and we're going to take it to base 2 to undo this log base 2 here. So we're going to take base 2 to both sides of our equation. We have to do it to every single term on both sides of our equation. So we're going to end up with, we're going to have 2 to the log base 2 of x plus 2 to the log base 2 of x minus 7. And then on the right-hand side, we're going to have 2 cubed. So we know that these guys are going to undo each other here. So we're just going to be left with x plus x minus 7 on the left-hand side of our equation, and then that's going to be equal to 8. So from here, it becomes pretty simple to solve this guy. We're going to combine like terms, so we're going to have x plus x, which will give us 2x, and in the same step, we're going to add 7 to both sides of our equation. So we're going to end up with 2x is equal to 15, and then to completely solve for x, we'll divide by 2 on both sides of our equation. So x is going to give us 15 over 2, which is going to be equal to 7.5. Now for the last several questions here, we're going to be switching gears a little bit. We're going to be looking at application problems. So for question 54, we're going to be looking at compound interest. So the formula for compound interest is given by this here, where A is going to be the amount in dollars that we're going to have after T amount of years. And P is going to be our principal amount, so the initial amount that we deposited. And then R is going to be our interest rate, and then N is going to be the amount of times that it's compounded per year. So for this problem, suppose that $3,000 is deposited at 3.5% and it's compounded quarterly. So the first thing that we want to do is figure out how much money will be in the account after 7 years. So we're trying to find A in this case. So for problems like this, it's always best to identify what pieces of information you do have. So we know that our principal is going to be $3,000. We know that our rate is going to be 3.5%, and then whenever we're dealing with formulas like this, we always want to convert our rate to a decimal. So this will be 0.035, and then N is going to be the amount of times it's compounded per year. So if it's compounded quarterly, then N is going to be equal to 4, and lastly, T is going to give us 7. So we want to find A after 7 years, so we're just going to plug in this given information. So we're going to have our principal times 1 plus our rate over 4, and this is all going to be raised to the 4 times 7 power. So let's try to simplify this as much as possible before plugging it into a calculator. In our parentheses here, this is going to end up being 1.00875, and this is going to be raised to the 28th power. So we can plug this into our calculator here, and this is going to end up being approximately this here. And so we're going to round to 3 decimal places again. So this is approximately how much money we'd have in this scenario after 7 years. Now for part B, in this case, we're trying to find T. We want to figure out how long it'll take the account to grow to $5,000. So everything else is going to stay the same, except in this case, we already know what the amount is going to be. It's going to be $5,000, and we want to find our T value, how long it would take. So let's plug in our known information into this equation. We're going to have A is equal to 5,000. Our principal is still 3,000. And we're still going to have this guy in our parentheses here. It's still going to have 1 plus our rate divided by 4. So this is going to be 1.00875, and it's going to be raised to the 4 times t here. So 4t. Now we want to solve for t. We want to figure out what this value is, so let's try to completely isolate t. The first thing that we should do is divide both sides of this equation by 3,000. So on the left-hand side, we're just going to end up with 5 over 3. And then on the right-hand side, we're going to have this here. Now we know that if we want to solve for a variable in an exponent or an exponential expression like this here, we can use our log properties. So let's take log on both sides of this equation here. So we're going to have log of 5/3. It's going to be equal to log of this guy. All right, so using our power rule, we know that this is going to be the same thing as, we still have this on the left-hand side, but on the right-hand side, this guy here is going to come down in front of our log. So we're going to have 4t times log of this decimal. Now from here, what's happening to t is it's being multiplied by 4 and by this log function here. So we can just divide both sides of our equation by 4 times this. All right, so t is completely isolated here, and it's going to be equal to log of 5/3 over 4 times log of 1.00875. Now we can plug this into our calculator, and we're going to get that t is going to be approximately 14.659 years. So this means it'll take just under 15 years for this account to grow to $5,000. All right, so for the last question in this section here, we're again working with an application problem. So suppose that the amount in grams of plutonium-241 present in a given sample is determined by this function here. So T is going to be measured in years, and what we want to do is approximate the amount present after 10 years. So this is an example of exponential decay. So the amount is decaying at an exponential rate. So we want to figure out the amount present after 10 years. So T is going to be equal to 10. And we can plug this directly into our formula. So we're going to have A of 10 is going to give us 2 times e to the negative 0.053 times 10. So this is going to be the same thing as 2 times e to the negative 0.53. Now we can just plug this directly into our calculator here, and so this is going to be approximately 1.177 grams. So this means after 10 years, there's only going to be about 1.177 grams left in the sample. So in the last section of this video, we're going to be going over graphs of rational functions. So we're going to start with these two questions here. We want to graph each rational function using reflections and translations. So for this first one here, we have f of x is equal to negative 3 over x. Now what's happening here is we have our parent function, this 1 over x. And when we're multiplying it by this negative 3 here, this minus sign is going to reflect the graph about the x-axis. And then this factor of 3 here is going to increase all of our outputs by this factor of 3. So essentially, each point is going to be 3 times as far away from our x-axis. So just to emphasize this, we're going to rewrite this as negative 3 times our parent function of 1 over x. Now, let's graph this parent function here just so we can see what's happening with this reflection and then this factor of 3 here. So our parent function, this 1 over x, is going to look like this here. If we were to plug in 1, we would get 1. If we were to plug in half, we would get 2. If we were to plug in 2, we would get half, and so on. And we actually have vertical and horizontal asymptotes here on the y and x axis. So our graph is not going to cross these asymptotes here. So our graph is going to look something like this here, and we're not crossing these asymptotes. And then on the other side here, let's say if we were to plug in negative 1, we would get negative 1. If we were to plug in negative 2, we'd get half, and so on. So here are some points here on the other side. So our graph on this side, in this third quadrant here, is going to look something like this. So this is the graph for 1 over x. And what's happening when we have this minus 3 out in front, again, we're going to reflect this over our x-axis here. So all of these points are going to be reflected over the x-axis, and all of these will be over here on this side. But we're also going to be multiplying our outputs by 3. So, for example, this point here is going to be reflected over our x-axis, so it's going to be here, but we're also going to multiply this output by 3. So this point's actually going to be this negative 3 here. So let's do this in black. So we'd have this point there. So let's repeat this process for the other points that we've graphed. So this is going to be reflected about the x-axis. So this is going to be right around here, and then we're going to multiply this output by 3. So it's going to end up being right around there at negative 6. And then our graph is not going to cross these asymptotes, so it's going to look something like this here. So doing the same thing for these points here, we're going to reflect this and then multiply the output by 3. So we're going to have a point here, we're going to have a point here, and so our graph again is not going to cross these asymptotes, so it's going to look something like that there. Alright, so let's do the same thing for question 11 here. Now in this case, we have our parent function, this 1 over x, but then this plus 1 on the outside tells us that we're actually going to be moving our graph 1 over x up 1 in the vertical direction. So, for example, we could just plot some points, and I'm not going to plot the parent function again, it just looks like this in green, and what's happening is all of these points are being moved up 1 unit. So, if we have the point 1, 1, we're going to move that up 1 unit. It's going to be right there. If we have the point 0.5, 2, that's going to move up 1 unit, right around there. Now the most important thing in this case when we are moving a graph in the vertical direction is that it's going to be moving the horizontal asymptote. So in this case, we're still going to have our vertical asymptote on the y-axis here. We know if we were to plug in 0 for x, it would be undefined. So that's why we have this vertical asymptote here for this function 1 over x. But when we are moving this graph up 1 unit, this horizontal axis that was on the x-axis here is going to be moving up 1 unit. All right, so the graph in this case is going to look just like this here. Now on the other side, we're going to have the same thing. So this point, for example, this -1 comma -1 is going to be scaled up 1 unit. So right here, we're going to have a point right here. So our graph, and then we'll have another one right here. So our graph in this case is going to look just like this here. So that's the main thing that's happening when we are adding or subtracting a value here on the outside of our parent function. It's going to be moving our graph in the vertical direction here. And then something else to note, when we're doing that, we know that's the case because at this horizontal axis here, this function would be undefined. There's nothing that would make this output here 1 because there's nothing that would make this guy 0. If this guy was 0, then we would get an output of 1 here, but we know we can't divide by 0, and the only way that a fraction like this would be 0 is if the numerator were 0. So since that can't happen, our output is never going to be this value 1 here. So that's why we're going to have this horizontal axis there. Now for this next question here, we just want to find the asymptotes of this function here. Now we have this polynomial in our denominator of this function, so the first thing that we're going to want to do is factor it. So factoring this guy, we're going to get 2x plus 3 times x minus 6. So from here, we can easily see what our vertical asymptotes are going to be. These are going to be the points that make this function undefined, so make our denominator equal to 0. We know that our denominator is going to be equal to 0 when 2x plus 3 is equal to 0 or x minus 6 is equal to 0. So we're going to get that x is equal to -3 over 2 or x is equal to +6. So we're going to have two vertical asymptotes in this case here. So at x is equal to -3/2 and at x is equal to 6. Okay, so these are our vertical asymptotes. Now we also want to find our horizontal asymptotes or if there are any oblique asymptotes in this case. So I've pasted this here, and this is directly from the book, and this is the procedure for determining asymptotes. So we already know how to find the vertical asymptotes, and that's what we've done for this example. Now we also want to see if there are horizontal or oblique asymptotes. Now, in order to determine this, we're going to be looking at the degree of the polynomials in our numerator and denominator of our function. So there are 3 cases here. So if the numerator has lesser degree than the denominator, then we're automatically going to have a horizontal asymptote at y is equal to 0. However, if the numerator and the denominator have the same degree and the function is of this form, then we can find the horizontal asymptote by dividing the leading term for both of these polynomials. And obviously, if these guys are actually the same degree, then they're going to cancel. We're just going to end up with the coefficients for each of these leading terms here. And then lastly, if the numerator is of degree exactly 1 more than the denominator, then there's going to be an oblique asymptote. So for this particular example, there's not one, but we will see an example of this in this video. So we'll save this procedure for later. So going back up to this guy, we want to see if there is a horizontal asymptote. Well, if we look at the degree of these guys, the degree of the denominator is bigger than the degree of our numerator. So we automatically know that we're going to have a horizontal asymptote at y is equal to 0. So these are our asymptotes for this function. Now for the last 2 examples in this video, we're going to be graphing these rational functions, and we're going to do so by following this step-by-step procedure from the textbook. So for the first 2 steps, we're going to be finding any asymptotes. So for step 1, let's find the vertical asymptotes of this guy here. So we have x plus 3 squared in the denominator. So this automatically tells us that we're going to have a vertical asymptote at x is equal to -3. If x is equal to -3 here, then this guy is going to be undefined. Now for the second step here, we want to find any horizontal or oblique asymptotes. And the way to do that is by looking at the degree of the polynomials in our numerator and denominator. So the first thing that we're going to do is expand on these guys. So I'm going to distribute this x to both terms in our parentheses here. So we're going to have x squared minus 2x. And in our denominator, we're going to FOIL this. This is x plus 3 times x plus 3. So this is going to give us an x squared plus 6x plus 9. So now we can easily see what the degrees are of these polynomials here. And notice we have the same degree in our numerator and in our denominator. So going back to this here, to determining our asymptotes, let's see which case we're looking at. So if the numerator and the denominator have the same degree and the function is of this form, then the horizontal asymptote is going to be the coefficients of the leading term in the numerator divided by the coefficient of the leading term in our denominator. So in this case, this would just be, we're going to have x squared over x squared. The coefficient for both of these is just 1. So we know we're going to have a horizontal asymptote at y is equal to 1. And we know we're not going to have any oblique asymptotes. Now going back to our procedure for step 3 and 4, we want to find the x and y intercepts. So we know to find the y-intercept, we're going to plug in x is equal to 0 into our function and evaluate. And then to find the x-intercepts, we're going to set the function or our y or our output value equal to 0 and solve for x. So let's do step 3 and 4 here. We'll do this in 1. Okay, so if we want to find our y-intercept, we're going to set x equal to 0 here. So we're going to plug in 0 into this guy. If we plug in 0, we're going to end up with 0 in the numerator, and we're going to end up with 9 in the denominator. So we know that this is just going to be equal to 0. So this tells us that our y-intercept is going to be the origin. Now for our x-intercept, we're going to set our output equal to 0. So we want f of x to be equal to 0. Now, since we're dealing with a rational function in this case, the only way that this guy is going to be equal to 0 is if the numerator is equal to 0. And we saw that in when we were trying to find the y-intercept. 0 divided by anything is 0. So again, the only way this will be 0 is if the numerator, or x times x minus 2 is equal to 0. So we know that x times x minus 2 is x squared minus 2x. So the only time that this is going to be equal to 0 is if x is equal to 0 or x minus 2 is equal to 0, so x is going to be equal to positive 2. So in this case, we're actually going to have two x-intercepts. So the x-intercept is going to be 0, 0, the origin, and 2, 0. All right, now for step 5 here, when trying to graph this, we want to determine whether the graph will intersect its non-vertical asymptote. So in this case, we want to figure out if this graph is going to intersect the horizontal asymptote. So in order to do that, what we're going to do is set our function equal to this horizontal asymptote and see if we have a solution. So for step 5 here, we're going to set our function. So this will be x squared minus 2x over this guy here. We're going to set this equal to the value for our horizontal asymptote, which is 1. Now from here, we just want to solve for x and see if we get a solution. If we do get a solution, then that'll tell us that it does intersect the horizontal asymptote at that particular point. So in order to solve for x, the first thing we're going to do is multiply this whole polynomial to both sides of our equation. Multiplying it on the left-hand side will cancel these guys out, and on the right-hand side, we're just going to get that polynomial times 1, which just gives us that polynomial. So I'm going to write this small. So from here, we just want to solve for x. So notice we have an x squared on both sides of our equation. So these guys are going to cancel. If we were to subtract 1 from one side to move it over, they would just end up canceling each other out. Now from here, we want to get all of our variable terms on one side of our equation. So I'm just going to subtract 6x on both sides, and then we'll keep that 9 there on the right-hand side. So we're going to have minus 8x is equal to 9. So we can easily solve for x by dividing by -8 on both sides. So this tells us that our x value is going to be -9/8 when we intersect that horizontal axis. And then lastly, the sixth step in this case is going to be to plot a few selected points as necessary. So maybe if we need a better idea of the shape of the graph. So let's plot everything else for now and see how far we can get. So let's do our asymptotes in this color here. So our vertical asymptote is going to be at x is equal to -3. So it'll be on this line here. And then our horizontal is going to be right here at y is equal to 1. Now next, let's plot our x and y intercepts. So our y-intercept is here, and our x-intercepts are there. So we have at the origin here, and then our second x-intercept is at this point, 2, 0. Another point that we actually already have is from step 5 here. We know that we're going to intersect this horizontal asymptote at the point x is equal to -9/8, and then our output value, if x is equal to this, is 1. So we have a point here at -9/8, 1. So we can plot that one as well. So that'll be somewhere around here. Okay, so now we want to see what the behavior of this graph is like on this side of our vertical asymptote. So that, in this case, we're going to use step 6 here and try to plot some points. So let's put in some values for x and see what we're going to get out. So there's not going to really be too many nice values in this case, but we want to see what's happening on the left side of this vertical asymptote. So I'm going to pick some negative x values. If I plug in -5, I'm going to get 8.75, and then -8 is going to give me 3.2. So these points are going to be, so we're going to have -5 and then 8.75, so somewhere around there, and then we're going to have -8 and then 3.2, so somewhere around here. And then we're not going to be crossing these asymptotes here, so on this side of our asymptote, the function is going to look something like this and continue on in this direction. These are the points there. And then on the right-hand side of our vertical asymptote, we know that the graph's going to behave this way. We're not going to go past the asymptote. And we know that we're going to cross the vertical one here. And we know that we're going to cross the origin because that's our x-intercept. We have to intersect the graph at that point. And we know that we're again going to intersect the x-axis at this point here. So it's going to move something like that. And then from here, we know we're only intersecting the horizontal asymptote at one point. We already had that point plotted, so the rest of the graph here is not going to cross this horizontal asymptote. So the graph of that function looks like this here. All right, so for this last question here, we're again going to be graphing this function using the step-by-step process that we saw in the last example. So the first thing we want to do is find the asymptotes. So we can automatically see that there's going to be a vertical asymptote at the value when x is equal to 1. So we're going to have a vertical asymptote at x is equal to 1 here. That's going to make this guy undefined. Now the second thing we want to find is our horizontal or our oblique asymptotes. So we're going to look at the degree of our polynomial in our numerator and denominator here. So notice the degree of this guy is exactly 1 more than the degree of the guy in the denominator. So going back to this here, let's figure out what kind of asymptote we're dealing with. So here for part C, it looks like we're dealing with an oblique or a slant asymptote. So to find it, we want to divide the numerator by the denominator, and then we're going to ignore any remainder that we get. So we're going to use our polynomial long division. So we want to divide our numerator, this x squared plus 2, by our denominator. So to do so, we know that we're missing this term here, right? Usually when we're writing our polynomials, we're going to write this in descending order. So we're missing our linear term or our degree 1 term. So when we're using polynomial division here, we're going to have to add this placeholder here for that missing term. And then we're dividing this by, let's move this over a little bit, by x minus 1. So following this process, the first thing we're going to do is divide these leading terms, and then our answer is going to go up here. That's the first term in our answer. Now we're going to multiply this guy by our divisor here, and then whatever we get, we're going to subtract out from this guy here. So multiplying this, we're going to end up with x squared minus x, and we're subtracting this whole thing. So these guys are going to cancel, and then we're going to end up with a negative times a negative x here. So this gives us a positive x, and then we're going to bring down this value of positive 2. Now repeating this process here, we're going to divide out the leading terms here. This will give us a plus 1, and then we're going to multiply that 1 here by our divisor and subtract it out. So we're going to end up, these x's are going to cancel here, and then we're going to end up with 2 plus 1, which gives us 3. So that means this solution here is going to be plus 3 over our divisor x minus 1, since 3 is our remainder here. Now going back to this chart here, remember we're going to disregard any remainder, and we're going to set the rest of the quotient equal to y to obtain the equation of this asymptote. So if we disregard this remainder here of 3, our equation is just x plus 1. So that means our oblique asymptote in this case is going to be y is equal to x plus 1. So we'll abbreviate this as OA. All right. Now for our third and fourth steps here, we're going to find our intercepts. So to find our y-intercept, we're going to set x is equal to 0 into this function. Now doing so, we're just going to have zeros here, so we're going to end up with 2 divided by negative 1, which is going to give us a negative 2. So our y-intercept is going to be 0, negative 2. Now for our x-intercept, we're going to set our f of x equal to 0. So we're going to have x squared plus 2 over x minus 1 here. Now we want to figure out which, actually, we're only going to set this equal to our numerator, right? The only way that this guy is going to be equal to 0 is if our numerator is equal to 0, because 0 divided by anything gives us 0. So we're just going to have this here, and we want to figure out for which x values this statement will be true. So the first thing we're going to want to do is subtract 2 on both sides of our equation here. So we're going to end up with negative 2 is equal to x squared. Now from here, if we want to solve for x, we're going to have to take the square root on both sides of this equation. But then we're going to end up with the square root of a negative 2. So we're not going to end up with a real number as a solution. We're going to end up with an imaginary number. So in this case, we're not going to have an x-intercept since we have no real solution. So since we have no real solution as in a real number, we're going to have no x-intercept. All right. Now for step 5 here, we want to figure out if our function's ever going to intersect our asymptote, our oblique asymptote. So what we're going to do is set this function equal to our equation for our oblique asymptote. So x squared plus 2 over x minus 1, and we want to figure out if this is going to be equal to our oblique asymptote of x plus 1. And actually, we know that this is never going to happen because here on the right-hand side, we showed that if we wanted to divide these guys, we're going to end up with x plus 1 and a remainder. So we automatically know that these will never be exactly equal to each other. We still have this plus 3 as a remainder. So this will never happen here. And we showed that by dividing these guys here using our polynomial long division. And then lastly, for step 6, we might want to plug in some points and see the behavior of this guy because we really only have one point here, this y-intercept. So we're going to plot some points for step 6 here. Let's plug in some x values and see what we get out. So if I were to plug in negative 2 into this function, I'm going to get a negative 2 out, so that's a nice number here. Let's see what happens if I plug in a negative 3. Doing that, I'm going to get negative 2.75. If I were to plug in a positive number, let's pick 2, this gives me 6, and if I were to pick 4, this also gives me 6. So these are some points that we can plot to see the behavior of this guy. So the first thing we want to do is draw our asymptote. So we're going to have a vertical asymptote here at x is equal to 1, and then we're going to have our oblique asymptote at y is equal to x plus 1. So we know that this is just going to be a line that has a y-intercept of 0, 1 and a slope of 1. So this is just going to look like this here. So this is our oblique asymptote, and we know that we're not going to cross this guy. All right. Now we have our y-intercept, so let's plot this here. This is going to be 0, -2, so we're going to have a point right here. We're going to have another point at -2, -2. And then we'll have another point at -3, -2.75. So right around here. And we know that this guy is not going to cross our asymptotes. So the graph of this guy is going to look something like this here. Now our other points, we have 2, 6 and 4, 6. So that's going to be a point here and then a point here. And we also know the behavior of this guy. We're not going to cross these asymptotes here. So this graph is going to look something like this, not passing these asymptotes. All right, so that'll be it for this video.